Okay, so now let's do an example of finding the points of inflection on our graph. Remember, that is where the second derivative is equal to 0. It can look like either one of those three graphs that I have up there. So the first thing we're going to do is find the second derivative and set it equal to 0. So pause the video. What I want you to do is change this to 8x squared. So the function should be 2x to the fourth minus 8x squared plus 3. And that is your f of x function. Now go ahead and pause the video, find the second derivative, see if you can figure out those points of inflection and where it's concave up, concave down, all without graphing. Okay, so when we find the first derivative, you get f prime of x is equal to 8x to the third minus 16x, and then find that derivative, you get 24x squared minus 16, set that equal to 0. Then you divide each side by 24, and you get x squared is equal to 16 over 24. Take the square root, and that's what all of this down here is. So positive and negative. Don't forget the positive and negative when you take the square roots of something. Of 16 over 24, square root of 16 over square root of 24. So you get positive and negative. You could probably stop here, but you can't technically have a radical in your denominator. So I went all the way to here. But this is approximately 0.8. Positive and negative 0.8 is what we're looking at. Now, those are our points of inflection. So what we can do is to determine concavity. So negative 0.8 and positive 0.8, that's where it changes concavity. So we are going to look. So here's negative 0.8 and here is positive 0.8. So we can look at 0. Let's look at negative 1 and 1. So the second derivative at negative 1, the second derivative at 0, and the second derivative at positive 1. Go ahead and compute these. Again, all we care about is if they're positive or negative. Okay, so then when you plug those in, plugging in negative 1 into your function here, you get that is positive. So up to this point, that 0.8, it's concave up. So it's looking like this. And then between negative 0.8 and 0.8, it's negative. Because when we plug 0 in there, you get that it's negative, so it's coming back down. So its concavity is down. And then it changes back to positive after 0.8. So our graph looks something like this. Now where it's at on here, it's hard to tell, but it's going to look something like that. In fact, here's what the graphs look like. Turn that one off. Here's what the original graph looks like, and you can see the point of concavity right around in here at negative 0.8 and 0.8. And then when we include, there's our second derivative, you can see at that point around where we said negative 0.8 and 8, that's where they cross over. And so it's going to be up here, right around there on that point. Anyway, you see here's the second derivative where it's 0 up here. That's going to be around negative 0.81 and positive 0.81 because this is the second derivative. Another example, go ahead and graph this and determine the intervals on where the function is concave up and concave down. So graph it. If you can't use the graph exactly, you might have to actually find the second derivative on this one to help answer that question. Okay, so here you have your graph, and you can tell that it's going to be somewhere in here where that point of inflection is going to occur because it's concave up here. Then it goes somewhere in here. It goes from up to down and then down to up back in here. So we will have to actually go through, find the second derivative, set it equal to 0, and when we do that, you get positive negative square root of 1/12. So those are the points of inflection. So right here, those are our points of inflection. All right, because if you look at the graph and graph one of those, so right here, x is equal to square root of 1/12, right there is a point of inflection. And then over here on the other side is your other point of inflection at negative square root of 1/12. Okay, so those are your points of inflection for that particular graph. And so your graph should look something like this with those points of inflection. And then also you would say that it's concave up because it's asking for what intervals, right? Is it going to be concave up or concave down? So it would be concave up from negative infinity up to that point, negative square root of 112, and from square root of 112, oops, that's a 12, to infinity. And then it's going to be concave down between those. So from negative square root of 112 to positive square root of 112 is where it's going to be concave down. So you can also use the second derivative to find whether or not the extrema, which we've been talking about as well, whether that's an extrema of a minimum or a maximum. So for example, if you find the second derivative at a critical point, that's very important. If you find that it's greater than 0, or remember that means concave up, then it's a minimum. Because remember, if a graph is concave up, it looks like this. And so if you find, you know that this is a critical point, and you put that in your second derivative, and you get a positive answer, it's concave up, your graph looks like this, that is a minimum. So if the second derivative, again, at a critical point, is less than 0, then it's a maximum, right? Because if it's less than 0, it's concave down, your slopes are decreasing. So right here's your critical point, and if the second derivative is less than 0, then it is a maximum point. So let's try that on here. So first of all, find the relative extrema. Remember the relative extrema, those occur when your first derivative is equal to 0. So find those extrema first, and then use the second derivative to determine whether or not it's concave up or concave down at those points. Pause the video, try it on your own, and then come back. Okay, so then when you go ahead and solve this first derivative, set it equal to 0, it factors in x minus 1 and 3x minus 7. So set both of those equal to 0, you get x equals 1 and 7/3. So these are your critical points. That means if the extrema are going to occur, they're going to occur at those points. All right, so now we're going to test it using the second derivative. So find the second derivative, and that gives us 6x minus 10. Now all we care about is whether you get positive answers or negative answers when you plug in 1 and 7/3. Plug them right into here. Okay, when you plug in 1, you would have 6 minus 10, which is a negative answer. When you plug in 7/3, so that is about 2 1/3, right? And that gives you, let's say even if it's 2, that would give you 12 minus 10, which is a positive answer. So at x is equal to 1, since it's concave down, that is a maximum. And at x equals 7/3, that since it's concave up, second derivative is positive, it's going to look like that. That is where the minimum occurs. Okay, and again, you can look at the graph. I didn't graph this one. Whoops. But if you need to check it, you can look at the graph, but you'll see the concavity can help us make it a lot simpler. Then remember the first derivative test, you had to test all those points around there, whereas if you just jump to the second derivative and determine the concavity, it might be a little bit easier. That is the end of this video. I hope it makes a little bit of sense. If not, rewatch the videos.